Assalamualaikum and hi, my name is Zikri bin Hasni. Today I would like to share to you about our subject MMK 21103, which is Computer Aided Engineering, with the title of Redesign and Analysis of Aircraft Engine Bracket. My group is Group 19 from UR 6521004 for Product Design. This is my group member. First of all, me myself, Zikri bin Hasni, matrix number 231403998. Next, we have CHEANG ZHUANG, matrix number 231404007, and last but not least, we have WAFIQ FITRI and ANOR, matrix number 231401067. This is the introduction with our title of Redesign and Analysis of Aircraft Engine Bracket. The aviation industry demands lighter, stronger, and more sustainable components to enhance fuel efficiency and reduce emissions. One such component is the aircraft engine bracket, which, while passive during flight, is critical for engine maintenance. This project aims to redesign the bracket using aluminum alloy as a sustainable alternative to titanium, targeting lower environmental impact and material costs. Using computer-aided design and computer-aided engineering tools, we optimize the design to reduce mass below 0.8 kg while maintaining structural integrity. To ensure safety and performance, we conducted three kinds of analysis. First, linear static analysis to evaluate stress and deformation. Second, we have thermal stress analysis for under temperature changes. And last but not least, which is free vibration analysis to determine natural frequencies. The final design supports SDG12, which is responsible consumption and production, by minimizing material usage without compromising safety or functionality.
My name is KHAI. Normal matrix is 231404007 from UR 6521004 product design. Now I will present the CAD design for this group by each group member and presenting the linear static together. Before presenting the data, I would like to mention the requirement for the model design of the mass is lowered at 0.8 kg. For our CAD design, our group member all are using the aluminum as our material. Thus, for the first member design is by FITRI. Based on the design and data given after analyzed by ANSYS, the first design was successfully hit the requirement with the mass 0.7691 kg. For the second design was failed because of the mass are over higher than the requirement, which is 0.82152 kg. Besides that, the second group member of the design is by CHEANG. The design 1, model 3 is successfully hit the target of the requirement with the mass 0.67829 kg. For the second design, model 4, it also is successfully hit the target of the requirement with the mass 0.75579 kg. Next, the third group member design is by Zikri. Design 1, model 5 is successfully hit the target of the requirement with the mass 0.70861 kg. The second design, model 6, is also hit the target of the requirement with the mass 0.79953 kg. As a conclusion for the linear static analysis, based on the 6th design model, the model 2 was a failed design with the mass 0.82152 kg. On the other hand, from the 6th design, the model 4 was the best that successfully with the mass 0.75579 kg. So this is about the result for the equivalent bond mixture stress. This is the result for the total deformation result. So this is the factor of safety result by the ANSYS. And this is the figure of the proof that mass of bracket for design model 4. In this slide, I will present about the data present design and comparison between the original bracket and present bracket. And beside is the percentage difference for each criteria. So the criteria that we have is about mass, FOS, and the deflection. For the target value, the mass that we get is below the 0.8 kg. for the FOS in the range of 1.2 until 3. For the target value in the deflection is below N 0.35mm. For the parallel design that we get, the mass is 0.75579 kg. For the FOS, by using the formula, yield strength divided by the maximum work missile stress that we get is 0.8713. So for the deflection for present design is 0.22703 meter. So let's be seeing about the comparison between the original bracket and present bracket. So the mass between the original bracket is about 2.505 kg. For the present design is 0.755079 kg, 2.8713. For the deflection, for the original design is 0.43mm and the present design is 0.2703 meter. So besides that, let's see the mass percentage difference that we get is about the 5.5 to 7%. For the FOS, percentage difference that we get is 139.275%. The last for the deflection, percentage difference is 35.134%. So this is the data for the static analysis that we get.
Now, we will look for the thermal stress analysis. This is the picture from the ANSYS workbench, which shows the initial temperature is 25 degrees Celsius. The initial temperature is the static heat level of a system before thermal stress is applied. It affects how material expand, contract, and respond to temperature changes. It also the impact on results, which a higher or lower initial temperature changes stress predictions and system performance. In the real-world example, engineers use it to design safer bridge, electronics, and engines that handle heat better. So, setting the right initial temperature ensures accurate and reliable thermal stress. The final temperature of 75 degrees Celsius for an aircraft engine bracket in our thermal stress analysis might seem low compared to typical engine operating temperatures, which can reach 100 to 150 degrees Celsius or higher. This is the reason why, for the possible reasons of our final temperature, which is 75 degrees Celsius. First, component locations. Not all parts of an aircraft engine are exposed to the higher temperatures. The bracket might be located in a cooler region where temperatures are moderated. Second, material limitations. If the bracket is made of aluminum, its operational limits are lower than superalloys. Aluminum alloy typically lose strength above 150 to 200 degrees Celsius, so the analysis might conservatively assume a lower temperature to avoid material degradation. Third, steady-state versus transient analysis. 75 degrees Celsius could represent the steady-state operating condition rather than peak transient temps. ANSYS analysis often starts with simplified, conservative assumptions before modeling extreme cases. And the reason for is cooling effects. Aircraft components are oftenly actively cooled. The bracket stem could be suppressed by cooling mechanism. While we did not use 100 to 150 degrees Celsius, if the bracket were near the combustion chamber or exhaust path, 100 to 150 degrees Celsius would indeed be plausible. However, this analysis might exclude these zones due to first, boundary condition simplification, which focusing on a less critical component, and last, material safety margins to avoid thermal creep or distortion. This is the thermal stress results, which we create the table of two comparison, which is without temperature and with temperature. Here we can see equivalent bond missile stress, total deformation, and factor of safety. Why do we compare these two? First, to see the impact of heat, which shows how much stress and safety change just from temperature. Second, to spot hidden risks. For example, stress jumps 4.6 times from without temperature, which is 97.517 into 451.27 with temperature megapascal. Second, we spot hidden risks from safety drops 78%, which from the without temperature is 2.8713 into 0.62047 with temperature. And last but not least, we want to see if it's a fixed or fail. For example, if numbers get worse with heat, the design needs improvement, which is better materials or cooling. Now we will move to the free vibration analysis. This analysis reveals the natural frequencies and mode shapes of the aircraft engine bracket, providing insight into its dynamic behavior without external forces. The result helps assess structural stability and identify critical vibration modes essential for evaluating overall performance. This is the natural frequency and total deformation results. This is the table that puts 6 modes of the natural frequencies and also the total deformations. Now I will explain to you from mode 1 to mode 3 of the transitional modes from the free vibration analysis. Mode 1 is the X translation. It moves side to side motions. Mode 2 is a Y translation. It moves front to back motion. And mode 3 is a Z translation. It moves up and down motion. And this is the mode 4, 5 and 6, which is a rotational mode or twisting movements from the free vibration analysis. Mode 4 is an X rotation. It twisting like a wing rolling. Mode 5 is a Y rotation. It is nodding like a car tilting forward. And lastly, mode 6 is a Z rotation. It's yawing like a steering turn.
So for the conclusion of this aircraft engine bracket project, the key achievements here is the material changes, which when we replace the titanium alloy with the aluminum alloy, it can reduce the weight and also the environmental impact. So for the best design here is the project 4 made by CHEANG, which met all the design targets. So for the performance comparison table, we can see here there are 3 criteria, which is mass in kilogram, the factor of safety, and also the deflection. The original design having a mass of 2.05, the FOS is 1.05 and the deflection is 0.43. So the best redesign made in this project is the project 4, which is owned by CHEANG. The mass is 0.75579 kg. FOS is 2.8713, which is hugely higher than the original design, and the deflection is 0.22703 mm. So for the summary, the thermal stress analysis is having a temperature changes range from 25 degrees Celsius to 75 degrees Celsius, and the stress is increased to 451.27 megapascal. The FOS, factor of safety, dropped to 0.620 in hotspots, which here we can see it is suggested for the needing of thermal relief design. For the free vibration analysis, the first to 6th model is having a frequency of 3243.4 Hz to 11,020 Hz, and all above the operational vibration range will be guaranteed for a low resonance risk. On to our next slide. It is the insights for engineers. There are 3 points here, and the first one is combining computer aided design CAD and computer aided engineering CAE leads to a safe, sustainable and lighter aircraft parts. So for the second point, the early thermal and modal analysis helps prevent the future failure. And on to our last point, the analysis refinement, which is the change of mesh, material data and also the boundary setup is crucial for accuracy.